Hello, and welcome to a lesson on nonlinear systems. A system, remember, is two or more equations that we're looking at the same time. If the system is nonlinear, it just means that at least one of the equations isn't a line. Okay, so remember, a system means that we are looking at two or more equations together. So two or more equations at the same time, simultaneously, what is happening within this system. If we are looking at a non-linear system, then we are looking at one of the equations not being aligned. So at least one of the equations is not linear, is not a line. Okay? A solution to a system, now just like with linear or any other system that we're looking at, is going to have a value for each of the variables in the system. So your solution will contain a value for each variable in that system, and if indeed it is the solution to the system, then when you plug it in, it should make every equation true. So plugging in each value for each variable into each equation should produce a true statement. Now, if the only variables that are in your system happen to be x and y, then the solution is going to be a point or multiple points where the graphs intersect. So it could be a point or multiple points where the graphs intersect. Okay, so just to take you back to the linear systems where we started, if we were graphing a linear system, if we were to graph two lines, let's say here's our first and then here's our second, then the solution is the point where those two lines cross. Now we also looked algebraically at solving a system like that using substitution or elimination. Well, all three options are going to be the same for our nonlinear systems that we're looking at today. If we're looking at a nonlinear system, it just means one of the equations isn't a line. So maybe we're looking at a parabola and a line in our system. Well, we can still solve algebraically, so by hand using substitution and elimination, or we can solve graphically. We just might end up with more than one solution. So in the case here of this parabola and this line, we've got two places where they intersect. That's two coordinates, so an x and a y here, and a second x and y here, two different coordinates where plugging them into each of the equations is going to produce a true statement, because this coordinate here lies on the parabola and on the line, and this coordinate here lies on the parabola and on the line. Okay, so the point I'm trying to make here is that the nonlinear systems that we're going to be solving can be solved using the same three methods that we started with linear systems: graphing, substitution, and elimination. Fortunately, for a nonlinear system, we won't be using matrices. That's all for linear stuff. That's when all your variables have a degree of 1. So no matrices here, just graphing, substitution, elimination. Okay, let's start with substitution. Remember, with substitution, the goal is to get one equation with one variable by substituting in something that we know. So for example, here, and hopefully we recognize that this is a parabola. When you have a y to the first and an x to the second, it's a parabola and a line. So parabola and a line, just again, wrap your brain around this. Actually, I don't need all that. If we're looking at a parabola and a line, a couple of things can happen. So it's possible and most likely that your parabola and line will cross twice, meaning we're likely going to be looking for two solutions. However, it's possible that your parabola and your line don't cross at all, so there is still that no solution possibility. Or it's possible that your parabola has a line that is tangent. That's a word that you're going to hear a lot in calculus. Tangent meaning that it could touch at exactly one point, and then there would be one solution. Okay, so these are the options. Good to know the options if you recognize the equations up front. But what we're trying to use here again is substitution. So in this first equation, I can't do any solving with those two variables. But if I can get rid of one of them, I'd be in good shape. Now, if we know from the second equation that y is equal to 2x plus 4, then we can replace y in the first equation with what it's equal to. We can replace it with 2x plus 4, and that would give us one equation, one variable. So this substitution works really well when you have a variable that is already isolated. So if I know y equals 2x plus 4, then I can replace all the y's I see everywhere else with the 2x plus 4. So if I rewrite my first equation, it's going to be x squared minus 4x plus, instead of y, I'm going to substitute in 2x plus 4 because those two are equal. And then I still have a minus 3 and an equals 0. And this equation we should be able to solve. So let's clean it up a little bit. X squared minus 4x, the parentheses, I use them because it's good practice, but distributing a 1 here, not going to change the 2x or the 4. So I'm just going to bring those terms down, and then let me combine like terms. So I have an x squared minus 4x and positive 2x. Let me change colors there. Minus 4, positive 2 is going to leave me with a negative 2x. And then positive 4 and negative 3 is going to leave me with a plus 1 here, equal to 0. And we can solve this by factoring. There are factors of 1 that make negative 2. Factors of 1 that make negative 2 would be negative 1 and negative 1. And dividing those by the leading coefficient of 1 wouldn't change. And so this is going to factor into an x minus 1, x minus 1, which means our solution is the same solution twice. That means we would see a parabola that bounces. Remember the multiplicity of 2 there. So a solution of 1 twice, but x equals 1. Now remember, that's just one part of our answer. We have to figure out the y value that goes with that x value. So once we find our y value, we've got to plug it back in. So plugging back in, let's see, I've used all my colors. So I'm going to plug this back in. I guess I can use gray. So now x equals 1 gets, it doesn't matter which equation we plug back into, although it would be very easy to plug into the second one to solve for y. So if I plug back in, I know y has to equal 2x plus 4, but we just found x was 1. So y is going to equal 2 times 1 plus 4, which is 2 plus 4, or 6. So we have one solution. Our one solution is at 1, 6. So if I was to graph this line and parabola, and I'll just confirm my work because it's easy enough to do with Desmos, these should be crossing at 1, 6. So x squared minus 4x plus y minus 3 equals 0. There's a parabola. And then y equals 2x plus 4. And there it is. And then that's one of those situations I told you where you have a line that's tangent. That means it's touching at exactly 1 point, and there it is, 1, 6. Okay? Now I know the graphing was a lot easier to solve, but this is algebra that you should be able to handle. Okay? I think this would be a good opportunity for you to try this one. Now, you probably don't recognize this equation in this particular course we haven't talked about. What you get when you have an x squared and a y squared term in your equation. I'm going to give you a quick little rundown, okay? We used to have a unit in college algebra for what we call conic sections. They've taken it out of the curriculum, so you're going to see this at some point. But if you have if you have an x squared in your function, that produces a parabola, right? Well, if you have a just a y squared, so let's say a y to the first and then an x to the first here. So if you have a y squared, it produces a sideways parabola, okay? If you put in an x squared and a y squared, an x squared makes a parabola, a y squared makes a sideways parabola. If you have an x squared and a y squared, then think about two parabolas, right? You got a parabola here, you got a parabola here. If you put them both together, a couple of things can happen. So you can make them go the same direction, and you could get this elliptical shape, or it could be sideways with this elliptical shape. And that's going to be if our coefficients are different here. Now, if the coefficients are the same, so if it was a 1x squared and a 1y squared, or 5 and a 5, or 3, or whatever it is, then it's actually going to make a circle. But think about two parabolas like connecting together, okay? Now, if they have opposite signs, your parabolas could go opposite ways. So you could have a graph that looks like this, or you could have a graph that looks like this, which is crazy. These are called hyperbolas. This is called an ellipse. Obviously, this is a circle. And that's all stuff that you used to see in college algebra. Anyway, it doesn't matter if we don't recognize the equation. We should still be able to handle the algebra here. So let's try this algebra. We know in this case that x is equal to 3y minus 3. So I need to substitute x with 3y minus 3. Now that's going to happen in two spots. I've got an x here that I'm going to replace, and I also have an x here that I need to replace. So both of those are going in. It's going to make this a lot of work for us. So instead of x squared, I'm putting in 3y minus 3 squared. And then I have a plus 5y squared, and then a plus 4. Instead of x, I'm putting in 3y minus 3. And then I have a minus 50y, and then I have a plus 3, and then equals 0. That looks like a lot of fun, right? So I just replaced both x's. I substituted in 3y minus 3 because x is equal to 3y minus 3. So let's clean this up. 3y minus 3 squared means I have to multiply it by itself. And let me just bring the rest of this down. I'm going to distribute here. So that's going to give me 12y minus 12. And then again, I'll just bring the rest of this down. Now I have to distribute here. So that's going to be a 9y squared. 3y times 3y is 9y squared. This is going to be negative 9y and another negative 9y, which gives me a negative 18y. And then lastly, negative 3 times negative 3 is going to give me a positive 9. And then again, I'm going to bring the rest of this down. And then I'm going to combine all the like terms that I can combine, because this is looking ridiculous. Okay, so we've got a 9y squared and a 5y squared, which is going to give me 14y squared. And then, let's see, I've got 18y's here and 12y's here. And okay, so all those y's, negative 18 and 12 and negative 50, and I just don't want to screw anything up. So negative 18, positive 12, and what was the last one? Negative 50. And that's going to be negative 56. So a negative 56y, and then what do we got left here? We've got positive 9, negative 12, and negative 3. So 9 minus 12 would be a negative 3, and then a negative 3 and another, oh, that's a positive 3. Goodness. Guys, look what I almost did. Okay, sorry. That's a positive 3. That's good. That makes this a little easier, because positive 9, negative 12 makes negative 3, and positive 3 is going to cancel. So if that cancels, that makes this really easy to factor, because these two guys got a GCF in common. 56 actually divides by 14 4 times. So we're going to take out a 14 and a y here, which is going to leave me y minus 4. And that means we get two solutions for y. So this first factor tells me that y has to equal 0, and this second factor tells me that y has to equal 4. Okay? So we're part way there, which is already a mess, but now we have to plug both of those in to find the x's that correspond. Remember, we're looking for intersections in a graph, so points. There's got to be an x and a y that go together. So I'm going to plug in. Let's take the y equals 0. It's going to be easiest to plug into our second equation here. So we have x equal to 3y minus 3, right? Well, we just found one of our y values was 0. So 3 times 0 is 0. 0 minus 3 is going to be negative 3. So when x is negative 3, y is 0, or when y is 0, x is negative 3 is one of our solutions. And again, x is equal to 3y minus 3. This time we're going to plug in negative 4. So 3 times, was it negative 4? Positive 4. 3 times 4 minus 3, that's going to be 12 minus 3, which is 9. So when y is 4, x is 9, or when x is 9, y is 4, means we've got two solutions here. So we have 2 points where these graphs would cross. We have solutions at negative 3, 0, and at 9 and 4. So if I plug both of those points into both equations, it's going to give me true statements, or if I graphed, those are the 2 points where these two graphs would cross. So let's just verify, because we can. All right, let's see. x squared plus 5y, I said 5y squared plus 4x minus 50y plus 3 equals 0, and then x equals 3y minus 3. And looks like, okay, so there you see the elliptical shape I was talking about, and you see the line that goes through it. So we have two solutions. They're crossing at negative 3, 0, and 9, 4, which was exactly what we said. So we're good. Okay, so that's substitution. Substitution works again nicely when you have a variable all alone. Now, if you look at the next system here, there's no way we're going to use substitution because no matter what variable I pick to get it alone would create a mess. This one is better suited for elimination, where we can add our equations together to get rid of a variable. Now, it'd be pretty easy to eliminate the x squareds if I multiplied the first equation by a negative, so that's what I'm going to do, or the second equation, it doesn't matter. But I'm going to multiply the first equation by a negative, which will give me a negative x squared, a negative y squared, a negative 16x, a negative 5y, and then a negative 63 equal to, still going to be a 0 there, which is good. Because now when I put these together, what's going to happen is a whole bunch of stuff cancels, right? The x squareds cancel, the 16x and negative 16x cancel, and the 63s cancel. So what we have remaining is 17 minus 1, or 16y squared, and then 85 minus 5, which is going to be 80y, and then equal to 0. And again, this one's pretty easy to factor since there are only two terms. It's just a GCF problem. And 80 divides by 16 5 times. So if you take out the 16 and the y, we're going to be left with 1y plus 5, which means here that y has to equal 0, and here that y has to equal negative 5. Now again, that's just a part of the solution. We still have to plug in to find the parts that go with it. And that's where this one gets pretty tricky, okay? Now, this is going to be a circle, this is going to be an ellipse, but you know, without background knowledge, how are you supposed to know that, right? So we don't really know how many solutions we're looking for here. So let's plug in the 0 first. I'm going to plug in the 0, and neither one of those equations looks really nice to plug into. I'm just going to go with the first one, plugging in a 0 for y. So let's see, if we have x squared plus 0 squared plus 16x plus 5 times 0 plus 63 equal to 0, what are we going to end up with? So that's plugging the 0 in first. And let me just connect these guys. Plug in this guy in to the first equation. So if we continue here, x squared plus, well, 0 squared 0, so 16x. 5 times 0 is 0, so that goes away. And then plus 63 is a quadratic left for us to solve. And this is factorable. Let's see, factors of 63 could be 9 and 7, and those make 16. So this is going to factor into x plus 7 and x plus 9, which means here that x has to equal negative 7, and here that x has to equal negative 9. So when y equals 0, x could be two different things. So this means that when y is 0, x could be negative 7, and this means that when y is 0, x could be negative 9. So that's two x's corresponding with that y. That's two different points where these graphs cross, okay? Now we're part way there. We still have to plug in the y equals 5. So let me go here. I'm going to hopefully not run out of space. I'm going to plug in the y equals negative 5. Again, I'm going to use the first equation. It looks a little cleaner if you ask me. And geez, I think I'm going to run out of space. So I'm going to shift this up a little bit. Okay, so now I'm going to plug in the negative 5. See if I can fit that here. So I'm going to have x squared plus negative 5 squared plus 16x plus 5 times negative 5 plus 63 equal to 0. Okay, so x squared, negative 5 squared makes 25. 5 times negative 5 makes negative 25. and plus 63 equals 0. So these guys are going to cancel, which means we're left with exactly the same thing we had in the last one, okay? So the same solutions, same equation, x squared plus 16x plus 63 equals 0. Same solutions, because it factors the same way. So x equals -7 and x equals -9. But this time the y value is different. So when y is -5, x is -7. And when y is -5, x is -9. So 2 more solutions. So 4 total. Okay, we have solutions at, let's see, -7, 0, -9, 0, -7, -5, and -9, -5. Okay, we're going to see graphs that cross at 4 different places. So let's confirm that. We're going to get some crazy looking graphs. These are pretty crazy looking equations, right? So x squared plus y squared and plus 16. I swear I'm hitting the one. It's not. There we go. 16x plus 5y plus 60. Jeez. Equals 0. And there's that little circle. And now we have x squared and 17y squared and 16x and 85y and slowly getting there. There we go. Circle and an ellipse. Crazy picture, but we see 4 points where these graphs cross. -7, 0, -9, 0. -9, -5, -7, -5. So all 4 are confirmed. Okay? Now, obviously graphing is a lot easier than the algebra, but again, algebra is something you should be able to handle. We're just going to practice a few more here, not algebraically just by graphing, but I threw in a couple of special cases. So this is mostly because we aren't always going to recognize our equations, and it's good to understand what's happening on the graph. So let's go ahead and graph this next one using Desmos. Let's find our intersections. Do you recognize what is that? It's hard to recognize it in that form, but just think about it. If we were to get y by itself, we would have to divide the x over. And so what we're looking at is a rational function there. So it's a rational, and then the second one's actually a circle. But let's go ahead and put it in. xy equals -24, and x squared and y squared equals 52. And we're going to see, look at that. It's a crazy picture. So it's actually a circle. I just distorted it. But 4 solutions, okay? So we get a graph, just so you can have reference for later. Oh, hold on. We have a graph. So again, you can reference it later. That does this kind of... That's terrible. It's not... there we go. Let's try the shape tool again. That's not bad. Okay, and then we've got something like this. Oh, whatever. Okay, so your picture looks something like that. So there are 4 points where these graphs cross. Negative... Let's get this here. -4 and 6. And -6 and 4. And then down here is going to be 4 and -6. And lastly, 6 and -4. Okay, so those are your 4 solutions found on the graph of this weird looking system. Okay, now the next one we hopefully recognize we have 2 parabolas there. But let's go ahead and graph them, because no matter what, it's going to be the easiest way to solve. So we have y equal to, let's see, x plus 1 squared plus 3. So there's our first parabola. And then y equals negative x squared minus 2x and then plus 2. So here our picture is two parabolas that are intersecting at their vertices at negative 1, 3. So this solution is at negative 1 and 3. That's it. One point where those two parabolas cross. And again, just so you have reference for later, this was our picture. We had a parabola looking like this, and then we had another parabola that looked like this, and that one point was the solution. And here the 4 points were the solutions. Okay, next one. Let's see. Two parabolas again. So we have y equal to x squared plus 8x plus 9. So there's the first one. And then the second one. Oh, sorry, that's not two parabolas. That's a parabola and a line. I'm sorry. I know what a line is. Okay. Don't judge me. It's been a long day. All right, 1/2 x and then minus 7. Okay, so we have a parabola and a line, and we can see that our parabola and line do not cross. That means there is no solution to this system. There is no value for x and y that is going to be on both of those equations or make both equations true simultaneously. Nothing in common. So again, no solution to this system. So just again for later, you had a parabola. Where was that parabola? That was like this, and you had a line that was like this, and there's just no way those two are ever going to cross, and so no way we're going to get a solution for that system. And then you probably know what's going to happen on the last one, but I don't want to keep you in suspense. So let's see. Y equals x minus 4 squared plus 2. And there it is. Okay, let's graph the second one. Y equals x squared minus 8x and then plus 18. And same exact parabola. If we were to distribute this one out, distribute the x minus 4 squared and then add 2, we're going to end up with this one. It's the same equation twice, just one's in vertex form and one's in standard form. So if it's the same parabola twice and they're intersecting or technically overlapping at every single point, then there are infinitely many solutions. Infinitely many solutions. Okay? And remember, that's called a dependent system. The no solution one, that's called an inconsistent system. But this is the same parabola twice. Okay. There it is, guys. Nonlinear systems. Much better, much more manageable, I think, than the matrices. Again, hopefully you've got enough to get going on your practice. And as always, if you need some extra help, then just reach out. All right, guys, take care.